Okay, so let us start the lecture. So in the previous lecture, we were discussing about the regular singular point. What do you mean by regular singular point? If you have any standard differential equation of second order linear differential equation is of this form, and you have this x is equal to x0 is an singular point. What do you mean by singular point? If this p of x and q of x are not analytic at the point x0, and then you will have x into p of x and x square into q of x, sorry, x in minus x0 into p of x and x minus x0 square into q of x are analytic at x0, then we can say that this differential equation 1 has a regular singular point at the point x is equal to 0, or I can say x is equal to 0 is the regular singular point for equation 1. Fine. So once we have a regular singular point, we have seen the Frobenius method to solve a differential equation. So in the previous lecture also we have solved one example. In this lecture also I'm solving one example, and I will suggest that you guys also do the same calculation as I'm doing on my digital board. You should do in your notebook so that if I need a previous steps, you can follow that. Okay. So it is my request that you can open your notebook and pen and solve the example as I'm doing on my digital board, as you are listening in a classroom, in physical classroom, as you are doing in the same manner. I will suggest that you can able to do it here also. Fine. So let us start with the example. So question is, find the series solution for this x 2x square y double dash plus x y dash minus x plus 1 y equal to 0. So the question is to calculate what is the series solution for this differential equation. So let us write down this differential equation into its standard form by dividing both sides by 2x square. So that's why this is y double dash plus x upon 2x square y dash minus x plus 1 upon x 2x square y equal to 0. Now if you're comparing this equation, y double dash plus p of x y dash plus q of x y equal to 0, we get p of x is equal to 1 upon 2x and q of x is equal to minus x plus 1 upon 2x square. So what we can say is this p of x and q of x are not analytic at point x is equal to 0 because they are not defined at that point x is equal to 0. So we can say that x is equal to 0 is a singular point for equation 1. What is the equation 1? Is this equation 1 we have redefined. So now we have to check for a regular singular point, whether x is equal to 0 is the regular singular point or not. So for that you have to do this x into p of x, which is 1 by 2, because you multiply this p of x by x, it's left with 1 by 2, and x square q of x will be minus x plus 1 by 2, because x square is multiplied to this q of x, so it will left with this quantity. are, so we note that, not therefore, we note that this x into p of x and x square into p of x are analytic at x is equal to 0. So therefore, x is equal to 0 is the regular singular point for equation 1. Okay. Since it is a regular singular point, using the Frobenius method, we can write down or we can assume as a solution. So suppose that the solution will be, that is y equal to summation n running from 0 to infinity a n x raised to n plus m. This is the Frobenius series that we have discussed in the previous lecture, and which is valid in the neighborhood of x is equal to x0. So if this is there, then we can have the y dash, that is the first derivative of this, which will be n running from 0 to infinity n plus m into a n x raised to n plus m minus 1. And the second derivative, by taking the another kind derivative of the same, will have y double dash, which is n running from 0 to infinity n plus m into n plus m minus 1 am x raised to n plus m minus 2. Now substituting this value of y dash and y double dash into the equation 1. Let us write down what is the equation 1. We can write down here again. So we note that, or we know this, given that 2x square y double dash plus xy dash minus xy minus y equal to 0. You can just observe what is your equation 1. The equation 1 is this. So what I did is I just multiply this y into x, and so we can have this. Now we can substitute this value of y dash, y double dash and y into it. So we'll have 2x square. We already calculated y dash double dash, that is n plus m into n plus m minus 1 an x raised to n plus m minus 2 plus x into n running from 0 to infinity n plus m an x raised to m plus n minus 1 minus x summation n running from 0 to infinity an x raised to n plus m minus summation n running from 0 to infinity an x raised to n plus m equal to 0. So now we'll substitute, or we'll multiply this x square inside in the first term. So therefore we'll have 2x. So that 2 is also I'm multiplying inside. So it is 0 to infinity. 2 into n plus m minus 1 an x raised to n plus m plus summation n running from 0 to infinity. In the second term also I'm multiplying x2 inside. So that's why it is n plus m an x raised to n plus m. In the third sum, that you can see that this x is multiplied to inside. So it is minus summation n running from 0 to infinity an x raised to n plus m plus 1. Then it is minus summation n running from 0 to infinity an x raised to m plus n equal to 0. Now, once you got this step, you have to calculate what will be the lowest degree term into it. Okay. So that you can observe very well that lowest degree term is m plus n, because when I substitute n equal to 0 into the first summation, we'll have m plus 1. Here is also same quantity you will have. Here it will be n plus 1 you will have, because n equal to 0, it will m plus 1. Here it is x power m. Here is also x power m. So let me write down what is the lowest degree term here first. That means by putting n equal to 0 into this series. So we'll have 2 into m minus 1 a0 x raised to m. That is the things we got for the first one. What we got for the second one, we got it is m a0 x raised to m. In this summation, that is in this third summation, if I put, then that degree is not starting with n equal to 1. So that is not the term we require, that is x power m. It is x power m plus 1. So we are not writing any term of this. Now for this one, that we are writing, because it contains the x power m term. So that is a0 x power m. Let me write down all other quantity as it is. So the plus, the first term that we have this, that we are writing, n running from 0 to infinity, 2 into n plus n plus m minus 1 an x raised to m plus n minus 2. The second term, now it is start from not 0, it is start from 1, because the first term we already written here. Plus summation. This is also start with 1, the second sum. So that's why I'm writing both together. So plus n plus m an x power m plus n. Why it is minus 2? I have written wrongly. This is not minus 2. It is actually m plus n. So here I have changed that. It is not minus 2. It is x raised to m plus n. In the second term, we have also x power m plus n. The third term I am not writing here right now. The last term which we have here in this term, which is minus an into x power m plus n. This is also sum is start with 1, because for that 3 terms we have written that. And then lastly we have summation n running from 0 to infinity, which is of minus sign, an x raised to m plus n plus 1 equal to 0. So this is the things we got. Okay. This I can rewrite as 2 into m minus 1 plus m minus 1. So I'm taking common out a0 x power m into this 3 term. So all other terms I have just taken out this a0 x power m common. So we'll have this quantity. Plus summation. Now it will start from 1 to infinity. Here is also, you can observe this x power m is common out, and an is also common. So that's why we can rewrite this as 2 into m plus n minus 1, an is common out, plus m plus n minus 1 into an x power m plus n. Now here in this last sum, since this is start with 1, I want that this is also start with 1, so that I can combine both them. So what we can do, we just replace, instead of n, I'm just replacing n minus 1. Okay, so it's kind, the things is replace n minus 1 by k. So what will happen? N will be k plus 1. So when n is 0, a k start with, sorry, it is n plus 1. N plus, so it is minus 1. So when n is 0, k will start with 1. Okay, so just I'm changing the index. Instead of n, I'm just replacing n minus 1. So whenever n is there, how to substitute minus n minus 1. So that is n running from 1 to infinity. Now an will be n minus 1 x power m plus n minus 1 plus 1 equal to 0. So finally what we get is, if you simplify this quantity, the first term, you will have 2m square minus 2m plus m minus 1 a0 x power m plus summation n running from 1 to infinity 2 into m plus n, m plus n minus 1 plus m plus n minus 1, and I'm just writing the last term also together with this, which is also having the term m plus n. Since this is also having the term m plus n, that you can just see in the last term, minus 1 and plus 1 is cancelled out, so it is also of the power x plus m. So this whole bracket is multiplied with an minus an minus 1, and all this quantity is multiplied with x power m plus n, which is equal to 0. Because x power m plus n is now common in all the summation, and this quantity is multiplied with an, and that quantity is an minus 1. So we'll have this. So what we get is comparing coefficient both sides, coefficient of powers of x. We get what we will get if you compare the coefficient to both sides. So here you will have, that is the power of x power m, and that is the lowest degree term, and if you compare the lowest degree term, you will have the identical equation. So that is 2m square minus 2m plus m minus 1 into a0 equal to 0, which will gives you 2m is common from this two, so it is left with this quantity that you can verify, 2m plus 1 into m minus 1, and that will gives you m equal to 1 and minus 1 by 2. These are the two roots you will have. And the other equation is this, which we have written here. That is the other power of x power m. So we'll have another equation, that is 2 into m plus n. And you just observe that is m plus n minus 1 is here also. M plus n minus 1. So if I take common out m plus n minus 1, then what we got? Can you tell me? We'll have m plus n minus 1 inside bracket. This will be 2 into m plus n plus 1 into an minus 1 equal to 0. That is the another recurrence relation we got. And this summation or this recurrence relation is true for any value of 1, 2 up to so on, because the summation start with 1. Now we have to calculate the two independent solution. Since this m1 minus m2, what is m1 is 1 plus or minus plus 1 by 2, because this is m1, this is m2, is not an integer. Since this is not an integer, we have a two linearly independent solution by putting the value m1 equal to 1 and m1 equal to m2 equal to minus 1 by 2. So for m equal to 1, I need to calculate what is the situation we have. I'm calling this as equation 2. Now if I substitute m equal to 1 into this equation 2, then we will have, it is 1 minus 1, that is in the first term we have. So we'll have n inside bracket 2 into 2 plus n plus 1 into an equal to an minus 1. So therefore, an will be an minus 1 upon n into 2n plus 3. And this is true for any value of 1 to up to so on. So we can now write down for n equal to 1, what is a1, which is a0 upon 5, because if you substitute here n equal to 1, 2 plus 3 is 5. For n is 2, a2 we will have, it is a1 upon 2 into 7, but that is 2 into 5 into 7, that we can write down in this manner. N equal to 3, we have a3, which is a2 upon 3 into 9, but the value of a2 is a0 upon this, so it is a0 upon 2 into 3 into 5 into 7 into 9. So I can write this is 1 into, that is no problem with that. And if you go further, so if you go further by putting the value, what will be the an? Will be a0 upon, you can just see that the pattern, it is 1 here, 1 into 2, 2 into 3 into, sorry, 1 into 2 into 3. So in general, it is n factorial. Here, you will have another term is 5 into 7 into 9 up to so on. 2n plus 3 is the general term you will have. And this is true for any value from 1 to up to so on. So this is the value of an you will have. And by substituting this value of an into the this y is equal to summation n running from 0 to infinity an x power m plus n. That is the Frobenius series that we have. If I substitute this value, then we have the series will be a0 upon n factorial 5 into 7 into 9 up to so on 2n plus 3 into x power n, because m is 1 plus 1. And by putting, see, this expression is true for any value of a0 into r, because it is arbitrary constant. So in particular, I'm just taking this a0 is 1. So that's why we can have y equal to summation n from 0 to infinity a0 upon, sorry, a0 is 1 we have taken, so it is 1 upon n factorial into 5 into 7 into 9 up to 2n plus 3 into x power n plus 1. So that is the first linearly independent solution we get. We can call it this as y1. Now m equal to minus 1 by 2. That is the second solution we have to calculate. Second linearly independent solution. So we substitute m equal to minus 2 into this equation 2 that we already calculated here. So if I substitute m equal to minus 2 into that equation, what you will get? Let me write down here, and then the final conclusion I will write down later on there. So it is minus 1 by 2. If I substitute minus 1 by 2 plus n minus 1, the second bracket we will have 2 into minus 1 by 2 plus n plus 1 an equal to an minus 1. So the first thing that we will have it is n minus 2 by 3, because minus 1 by 2. So it is en minus 2 into 3 upon 3, and the second term that will gives you what you will get. 2 is multiplied inside, so it is minus 1 plus 2n plus 1. Okay, so it is actually answer is 2n. So finally what we get, and all the things is in denominator, so that 3 goes in the numerator. So we get 3, so an is equal to 3 an minus 1 upon 2n into 3n minus 2. Is everybody got the same thing, or somebody got the different quantity? Please check. It may happen that my calculation will be wrong. Okay, so please check by putting m equal to minus 2 into the equation 2 and verify whether you will get this quantity or different. This is, we have dated mistake. Minus 1 by 2 minus 1 is minus 3 by 2, not 2 by 3. See? So this is 2n minus 3 upon 2. And that 2 will get cancelled. So there is no 2n is there. So finally you will left with not this quantity. Yes, anybody have calculated, or every you sitting idle? Yes, anyone have calculated? This is an minus 1 n into 2n minus 3 and n running from 1 to up to so on. This is the quantity you will left. Now for n equal to 1, what is a1? A0 upon 1 minus 1, so it is a0 upon 1, so it is, I can say, minus a0. for n equal to 2, a2 will be a1 upon 2 into 4 minus 3. So it is a1 upon 2. But a1 is minus a0, so it is minus a0 upon 2. What is a3? Or what I can say, if I put n equal to 3, what will be the a3? That is a2 upon, if I put 3, then it is 3 into 6 minus 3, that is 3 into 3. And since a2 is this, which will be minus a0 upon 2 into 3 into 3. Now n equal to 4. If I substitute, what is a4 is a3 upon n, that is 4 into 2 4s are 8, 8 minus 3 is 5. So it is 4 into 5. And that will be minus a0 upon 5 into 4. Because 2 into 3 into 3 we have to write down. So it is 5 into 3 into 3 into 2 into 3 that we have. Just rewriting the same quantity in this manner. Okay. What will happen if n equal to 5 I have substitute? We'll have a5, which is a4 upon 5 into, you just calculate, 2 5s are 10 minus 3, 7. So we'll have 7 here. And that is minus a0 upon 3 into 4 into 5 into 7. This 7 goes here. And the things, another things we got it is 2 into 3 into 5. It should come 4. Five into 3, 3 into 4 into 5 is there, into 7, 2 into 3 into 5. Okay. Why it is not coming? 4, 5, 5, a0 minus a0, 3 into 4 into 5 into 7, and this is 2 into 3. Into 5. Okay. So in that manner, you will have the solution. That is a0 you have, a1 you have, an. So the Frobenius series, that is the second solution. Y2 is equal to summation and so on. Summation 0 to infinity an x raised to m plus n. But what is m? M is here minus 1 by 2. So it is an x raised to m minus 1 by 2. So this is a0 x raised to minus 1 by 2 plus a1 x raised to 1 minus 1 by 2, that is 1 by 2, plus a2 x raised to 2 minus 1 by 2, that is 3 by 2, a3 x raised to 3 minus 1 by 2, that is 5 by 2, and so on. If you substitute these values here, that is a0 is a0, a1 we have the value is minus a0 x raised to 1 by 2 plus a2, we have the value is minus a0 by 2. So this is minus a0 by 2 x raised to 3 by 2. A3 is a0 upon 2 into 3 into 3. So it is 2 into 3 into 3 x raised to 5 by 2 and so on. So this is the value of a0. This is solution is y equal to c1 y1x plus c2 y2x. See, y1 we already calculated here. This is your y1. And y2 we already have calculated, that is here. We substitute both this value here. So that is summation n running from 0 to infinity a0 upon n factorial 5 into 7 into 9 up to 2 plus 3 x raised to 2n n plus 1 plus c2 into this whole thing a0 x power minus 1 by 2 minus a0 x raised to 1 by 2. If you want a0 common, you can write down common. That is a0 by 2 x raised to 3 by 2 minus a0 upon 2 into 3 into 3 x raised to 5 by 2 and so on. So this will be the series solution for a differential equation which has a regular singular point. Can I give you one example as an exercise to do it yourself? And there are a couple of examples also written on my class notes. You can solve that also. 2xy double dash plus x plus 1y dash plus 3y equal to 0. So try to solve this differential equation by your own. So first you have to check whether this differential equation has a regular singular point or not. If it does not have a regular singular point, if it does not have a singular point, then we cannot go further. Okay. Yeah. If it is an ordinary point, if I have any ordinary point, x is equal to 0 is an ordinary point, then you can assume as a solution will be summation a n x raised to n. But it is not, then you have to do it something else. Okay, as the manner which we have did it earlier. So we have to do in that manner. So this equation can be written in this form. So you will have p of x will be x plus 1 upon 2x. Q of x is 3 by 2x. Since x is equal to 0, undefined, I'm not writing now all the details. You can write down by your own. Since this p of x and q of x are not analytic at point x is equal to 0, x is equal to 0 is an ordinary point. Sorry, x is equal to 0 is a singular point. Since it is a singular point, you have to check whether it has a regular singular point also or not. So it is x into px. X into px is x plus 1, which is analytic, obviously. And x square q of x, which is 3x upon 2, which is also analytic. So we can say that this x is equal to 0 is the regular singular point. So hence we have the solution, that is by Frobenius method. We can write down the solution in this form, n running from 0 to infinity an x raised to m plus n. Now we know what is y dash and what is y double dash. So I'm not writing again here, okay, because we already calculated that is in previous example. And then I'm substituting all this value of y dash and y double dash into the given differential equation this. The given differential equation I can rewrite in this form, that is 2xy double dash plus xy dash plus y dash plus 3y equal to 0. Now let me write down a value of y double dash and y dash and y into this differential equation. So we'll have 2x summation n running from 0 to infinity an m plus n m plus n minus 1 x power m plus n minus 2 plus x into summation n running from 0 to infinity. We have this second term m plus n an x power m plus n minus 1 plus summation n running from 0 to infinity m plus n an x raised to m plus n minus 1. And the last term is 3 into summation n running from 0 to infinity an x raised to m plus n equal to 0. Now this x you can multiply inside. So this we can rewrite as summation n running from 0 to infinity 2 into an m plus n m plus n minus 1 x raised to m plus n minus 1 plus summation n running from 0 to infinity m plus n an x raised to m plus n plus summation n running from 0 to infinity m plus n an x raised to m plus n minus 1. That is the another term we have. And plus 3 summation n running from 0 to infinity an x raised to n plus n. So first of all, you should write down what is the lowest degree term here. Okay. So the lowest degree term, you can observe that it is m plus n minus 1. Here is also m plus n minus 1. Here it is x power m. Here it is x power m. If I put n equal to 0. So hence, the lowest degree term you will have is m x power m minus 1. So I just write down that term here in the front. So if I substitute n equal to 0 here, we'll have 2 into a0 m into m minus 1 x power m minus 1 is there plus here is also n into a0 and in bracket x power m minus 1 you will have. Now the summation is start with 1 equal to, okay, so summation start with 1 equal to an m plus n m plus n minus 1 x raised to m plus n minus 1. The second summation is as it is. The third summation is changed. It will start with 1 to infinity. The third is also same as it is. Okay. Now what to do? To replace your term here and here, your summation should start with 1. So what you have to do, you have to replace your n by n minus 1. So if I replace n by n minus 1, instead of it will start with 0, it will now start with 1. Okay. So let me write down that again. So it is 2 into A0. A0 is also I'm taking common into this 2. So it is 2 into M1, sorry, M into M1, M minus 1 plus M. A0 x power M minus 1. The first summation as it is that I'm writing. The second summation, I have to start with 1 to infinity. And instead of n, I have to substitute n minus 1. So it is m plus n minus 1, a n minus 1, x power m plus n minus 1. Here it is as it is. The third term is as it is. So plus summation n running from 1 to infinity, m plus 1, a n x raised to m plus n minus 1. In the third also, I am doing the same thing, replacing n by n minus 1. So it is plus 3 summation n running from 1 to infinity, a n minus 1 x raised to m plus n minus 1 equal to 0. So hence we can write down now by comparing coefficient both the sides. Coefficient of power of x. That also I am not writing here. You should write by your own word. Identical equation we get here, that is 2m square minus 2m plus m equal to 0. So that will give you m square, 2m square minus m equal to 0, and that will give you m into 2m minus 1 equal to 0. So that is gives you m equal to 0 and m equal to 1 by 2. These are the two roots of identical equation you will have. And what are the other terms you can have? The other terms that you can observe that this is of the power x power m plus n minus 1, and all of them it is there. So hence the recurrence relation we can have, let me write down, that is m plus n, m plus n minus 1. That is the first quantity you have from this. Plus m plus n minus 1, a n minus 1 you have second term. The third quantity is m plus n, a n, that we have here. And the third one is 3 into a n minus 1 equal to 0. Okay. Here I can take common out from this two. That is a n plus 1 also common out, a n is also common. So what is left from this? Here it is left to m plus n minus 1 plus 1. And taking this two quantity on the other side, you can take it out other side. It is minus, and a n minus 1 is common from that. So it is m plus n minus 1 plus 3, a n minus 1. So finally, what we have a recurrence relation, that is a n equal to minus of m plus n plus 2, a n minus 1 upon n plus n. And here what is left? Here is left with 2m plus 2n minus 2 plus 1. So it is 2m plus 2n minus 1. and this equal or this recurrence relation is true for any value which is start with 1, 2, or so on. Now for since identical equation has a two roots, m equal to 0 and m equal to 1 by 2, and this m1 minus m2 is not an integer. Since this is not an integer, we have two linearly independent solutions. M equal to 0, we have the first solution. Let us write down that is what you will have. So what is this equation now? An equal to, putting into this equation 4 or whatever the number is. Okay. So put n equal to 0 or sorry 1 into this. What we get a, or let me write down in general. N equal to 0, you can substitute. Put m equal to 0 in 4. We have an will be minus n plus 2, an minus 1 upon n, 2n minus 1. Okay. Now for n equal to 0, so it is true for n equal to 1, 2 up to so on. So you have a1, which is minus of 3 into an minus 1 upon 1. So it is minus 3an minus, sorry, minus 1 may have a 0 also. So it is 0. Okay, so it is minus 3a0. N equal to 2, a2 will be, if I substitute n equal to 2 here, so it is minus 4 into a0, sorry, a1 upon 2 into 4 minus 1. 4 minus 1 is 3. So it is minus 4 upon 2 into 3 into minus 3 a0. So I can write down this is as 3 into 4 upon 2 into 3 a0. And so on. You can write down further terms. What is n equal to 3 a3 you will have. So can somebody tell me what is a3? By putting n equal to 3 here into this equation. Yes, so it is 5, 3 minus 1. So it is 2 upon 3, 6 minus 1, 5. A2 will be this one. You can substitute that value here. So in the numerator, you will have 3 into 4 into 5. Denominator, you will have 2 into 3 into 3 into 5. A0. Okay. So finally, what is the solution? Minus minus become plus. Now minus outside, barabar. Because it is a plus sign, now it is minus sign. Okay, so what is the y1? Which is summation n running from 0 to infinity a n x raised to m plus n, but m is 0, so it is a n x raised to n. So the series is a0 plus a1x plus a2x square up to so on. A0 is, if you want, you can take common out, which is 1. A1, value of A1, we have minus 3 A0. So it is minus 3x plus A2 is this 3 into 4 upon 2 into 3, which I can write down 2x square then it is minus 3 into 4 into 5 upon 2 into 3, 3 into 5, x cube and so on. So this is the first solution, which is y1. Same way, can I give you as an exercise to calculate for m equal to 1 by 2, because the another value of m we have calculated, it is 1 by 2. Here you can just see that. So can you calculate for m equal to 1 by 2 yourself? Yes, I need the answer yes or no. Okay then. So what should I understood? No one is giving me the answer. So what should I understood from this response? Should I do it or should not do it?
Sir will do it.
Okay, that's good. So it is easy, just need to substitute the value and expanding the recurrence relation. Okay. There are other examples is written in my class notes. You can just go through it and try to solve by your own. Okay. See, this is a matter of practice. If you do the practice more, this calculation will become easy for you. If you are not practicing of such type of examples, you will you will find it is difficult and complicated, but it is not. It is very easy to deal with. Okay, so that is my suggestion, that you at least solve 5 example each of such type series solution, at least 5 example by your own, and then any example is in front of you, you can able to solve that. Now the question is why this method is work. So for that we have a theorem, and this basically this theorem is a Frobenius method. So let me write down the statement of this theorem. So assume that x is equal to 0 is the regular singular point of the ordinary differential equation y double dash plus p of x y dash plus q of x y equal to 0. Since this is a regular singular point, we can have that this x, px and x square q of x are analytic function at neighborhood of or at the point x0. So it will have a valid power series expansion. So that I am assuming, and the power series expansion of x px and x square qx are x into p of x will be summation n running from 0 to infinity pn x power n, and x square q of x we assume it is summation n running from 0 to infinity qn x power n. So this thing we are assuming that it has a valid power series expansion and which is valid on the this region mod of x less than r for some r greater than 0. Also, I am assuming that m1 and m2 with the roots of identical equation. What do you mean by identical equation? You know that it is the lowest degree term equal to 0. Should I write that identical equation here?
Yes, sir.
Okay. So the identical equation that we have did it earlier, which is the coefficient of lowest degree term equal to 0. Okay, which was we have calculated in this manner. That is m into m minus 1 plus m p0 plus q0 equal to 0. P0 is this, Q0 is this, what when substitute n equal to 0. So this is the identical equation we have. This M1 and M2 are the roots of this two identical equations. Okay, so that I'm assuming. And then the objective is, or then it says that, so this is the requirement I need. It says that the equation 1, that is this, has at least one Frobenius series solution. See, here I'm assuming that M1 and M2, and M1 is a bigger than M2. Okay, that is also I'm assuming. So whatever the bigger value will have the solution to that equation that we are doing with A0 is non-zero equal to 0 on the interval 0 to r, where the summation a and x power n is convergent for this mode of x less than r. Okay, so this theorem says that if this x0 is a regular singular point, then the solution of this identical equation which has m1 and m2, then this will be the solution. Furthermore, this is very important that we are writing. Furthermore, if this m1 and m2 is not equal to 0 or positive integer, what I said is if it is not 0 or it is a positive integer, then the equation 1 has another linearly independent Frobenius solution which is y2 equal to x power m2 summation n running from 0 to infinity a n x raised to n, which is valid for all x between 0 to r, and this summation a n x raised to n is convergent for mod of x less than r. So what we are solving examples previously, all this example is based on this theorem. This theorem says that if you have this x is equal to x0 is a regular singular point, and then solution of that identical equation which has m1 and m2, then you can write down your solution into this form. And if this m1 and m1 minus m2 is not a positive integer or 0, then you can have another solution which is this. The more important question one can ask is, what will happen if m1 minus m2 is 0 or a positive integer? Then you have to find out what is the another linearly independent solution. One solution is already there, that is this. You have to calculate the another solution in different manner. Okay. So let us try to prove this one. I think so I cannot able to prove this theorem in another 30 minutes. So, and it is better that we can start this theorem with the fresh mind. So it is better that I can stop here and we will discuss the later on about the proof after, I think so, today is 25. Tomorrow we don't have any lecture, and officially I cannot take the lecture till 2nd of December. Okay, but what I will do is I may put it the lecture on the YouTube if it is possible. Okay, so you require a fresh mind to deal with this theorem. So I'm stopping here. If you have any question, you can ask.